pleasure to introduce you to Miguel A Maria-Solano. Miguel Angel is a talented last year PhD student in my group, working on the computational evaluation of enzyme allosteric properties and steric selectivity, as well as he's working in the design of standalone enzymes for enhanced function. So he studied biochemistry at the University of Murcia in Spain. And in 2016, he moved to my group at the University of Girona with a prestigious PhD fellowship from the Spanish Ministry of Research. He did in 2018 a short research stay at the Chica Lab. And now he's finishing and he's writing his thesis and is currently looking for new positions. So this is an excellent opportunity for him. Thanks, Miguel Angel, for your willingness to participate in the symposium, and we are looking forward to your tryptophan synthase talk.
Thank you very much, Silvia, for the introduction, and of course, all the organizers for giving me this great opportunity. So the work that I'm presenting today is about the studies about the conformational ensemble of tryptophan synthase and its link in protein function, but also in enzyme engineering. Okay, first let me introduce the enzyme. Is tryptophan synthase, that is an allosteric complex that consists in two different subunits, TRPA and TRPB. And basically the mechanism after the aldolic cleavage of the IgP in the TRPA subunit, the product of the first reaction diffuses along an internal tunnel to react with L-serine that has been previously bound to the PLP cofactor. And then the tryptophan is produced. What is most interesting of this enzyme is that there is an allosteric communication between the two different subunits where each subunit regulates each other along the catalytic itinerary, so both cycles are synchronized. The interesting reaction for industrial purposes is the TRPB reaction, because of the production of L-tryptophan derivatives are very interesting. But the TRPB reaction is very challenging to engineer because it's a PLP cofactor dependent and it involves multi-step mechanism involving at least 9 steps. And this is not the only problem in order to engineer a TRPB reaction because due to the allosteric coupling between both subunits, there is a loss in activity in the absence of the protein partner. As you see, for instance, in the case of Pyrococcus furiosus, there is a 3.2-fold decrease in the catalytic activity. And for biotechnological applications and for engineering enzyme properties, it's much more desirable to operate with monomeric entities instead of multimeric complexes. Arnold and co-workers addressed this problem and they applied directed evolution to the TRPB isolated subunit and they enhanced the catalytic activity almost or more or less 1 order of magnitude, successfully obtaining this TRPB standalone catalyst. I mean standalone because the loss of the activity as a consequence of the absence of the protein partner is recovered, but not only that, their variant works even much more efficient than the TRPB in complex. What is interesting also here is that most of the mutations that were introduced in the directed evolution rounds are distal mutations. So this indicates that the recovery of the activity might be induced by allosteric effects towards the active site. So we were interested to decipher the conformational dynamics of this allosteric complex, the isolated system, but also the standalone catalyst. But before to start showing the results, we have to thank all the crystallographers that have obtained multiple X-ray data showing that in TRPB subunit, there is an open to closed transition of this COM domain that is acting as a lead covering the active site, where the open states are basically found in X-rays in resting state, indicating its role in substrate entry and product release. And as long as the reaction progresses, you can find X-rays of partially closed and closed states, which indicates its role probably in accelerating the catalytic step. So we're interested in study the conformational ensemble of this transition, and to do that, we recover the free energy landscape as a function of this motion. But first, I'm gonna just briefly explain what is the free energy landscape concept. Well, in this context, enzymes can be seen as an ensemble of accessible conformations in solution, and according to its probability to be sampled, the conformations can be represented as a function of the free energy. And you see there are several local energy minima separated by energy barriers. And many studies support the idea that after the binding of the substrate or a protein partner, or even distal mutations, this population, this ensemble of conformations can be redistributed by a population shift. And as we see in this case, from the open conformation towards the closed conformations. So we basically, in our study, we reconstruct the free energy landscape of the COM domain open to closed transition. As you see, for instance, this is an example of a plot of our analysis. When you see the x-axis is based on the X-ray data from open conformations that would be the most open, the one, towards the most closed conformation that would be the 15, as you see here, the closed state. And the y-axis represents the RMSD deviation from the ideal path generated from the X-ray data. So now I'm gonna start to show some results. I'm gonna start for the TRPAs complex. And for simplicity, I'm gonna show these two catalytic steps, the resting state, and the Q2 intermediate that is a quite advanced step in the cycle. This is basically after indole coupling to the L-serine. If we look at the left, we observe that in the resting state, the most stable conformation, or more likely, are open conformations that is in line with its function for the substrate entry at this point. But also some partially closed states are also visited. If we look at the right, as long as the reaction progresses, there is a population shift towards partially closed states and also closed states. And as you see, the whole transition is sampled with the open and partially closed states equal in energy, but the closed state is a little bit higher in energy. We continued the analysis on the Q2 intermediate for the isolated system. And in comparison with the complex, we observe very restricted COM domain conformational dynamics where only one local energy minima is found. Additionally, these closed conformations are very deviated from the original path generated with RMSD values around 2 of the deviation, and a structural analysis of comparison of these two states indicates that the isolated system performs unproductive closure. Finally, we analyzed the free energy landscape of the directed evolution evolved variant, and we observed like there is a recovery of the conformational heterogeneity since open, partially closed, and closed states are visited again. And additionally, the stabilization of the great stabilization of the closed state is explaining the great activity or the higher activity that this evolved variant displayed. Then once we have finished with the analysis of the conformational ensemble, we are interested you know, if we can predict activating distal mutations by computational methods. Well, this is actually a very difficult task. In order to do that, we relied in residue by residue correlation analysis that these tools have been successfully applied before to study allosteric properties. And in a recent study, our group was targeting these tools in order to predict directed evolution mutations in the case of retroaldolysis, and they successfully identified many of the directed evolution positions. I cannot go into the detail of the workflow of this analysis, but basically the idea is that we collect the trajectory of the allosteric system, that is a complex that, in this case, sample the whole transition of the COM domain, and we analyze the trajectory in order to get the residue correlation and distance matrix of every pair of residue, which is used to construct the original network system. And then by applying the Dijkstra algorithm, we finally obtain the shortest path map. The meaning of this graph is basically like a fingerprint of the conformational dynamics of the enzyme, or it can be seen as the enzyme pathways that most contribute to the conformational dynamics, of course, in terms of correlation motions. So we applied this tool to the tryptophan synthase allosteric complex, and here you see the results. And among the 6 directed evolution positions, 2 are directly identified, 3 were performing persistent non-covalent interactions with many of the residues in the shortest path map that you see in blue. And 1 of the positions have a minor role since it was performing a negligible interactions with SPM residues. At this point, we can see that this approach can identify important residues that high contribute to the conformational dynamics of the protein, but still there are many residues to be targeted, for instance, in order to engineer any TRPV for a standalone function. So basically, what we are targeting now is to try to identify which of these residues should be mutated in order to tune the conformational dynamics for a standalone function in this case. I cannot go in a very detail of this, but we were inspired in this work by Professor Sterner, where they did an ancestral reconstruction of the TRPS, sorry. And the interesting result that I want to explain you here is that along the phylogenetic tree, from the last bacterial common ancestral toward the modern, there is a change in the allosteric effects exerted by TRPA subunit. You'll see it better here, and you see as from the NC3 node in the phylogenetic tree, there is a dramatic decrease in the activity in the absence of the allosteric partner. And this is why we are collaborating with the Sterner lab in order to try to engineer this system for a standalone function. In contrast, the last bacterial common ancestral shows the opposite behavior. It works much better as isolated than in complex. This is why we are analyzing the shortest path map of this last bacterial common ancestral that it's supposed to be already a standalone catalyst, but still we get 74 residues here that would be introduced in the NC3 sequence in order for a standalone function. And we decided to rely on the sequence comparison between the local bacterial, last bacterial common ancestral with the NC3 node. And by sequence comparison of the shortest path map residues, we find these 6 positions only these 6 positions different in sequence. So we were interested in testing this enzyme variant. And as you see, the SPM6 variant, where most of the mutations are also distal, increased near 1 order of magnitude the loss of the activity in the absence of the TRPA subunit by only testing one single mutant from a rational approach. Finally, the conclusions is that there is fine-tuned control of the open to closed conformational ensemble of TRPV plays a key role along its catalytic cycle. The distal mutations can recover the allosterically driven conformational ensemble. Computational prediction of distal mutations is possible through the correlation-based tools like the SPM shortest path map. And well, this is data that is already published and you can have a look if you want. And finally, the Ancestral, this shortest path map approach, when in combination with the Ancestral reconstruction, can efficiently decrease the sequence space to target standard function. So it's a nice tool. It's a nice approach to combine as a semi-rational approach for enzyme engineering. Of course, thank you to all the people from the group, especially Silvia, Osuna, and Javier Iglesias that are involved in this project. This is Silvia and Javi. And of course, the collaborators from the Regensburg University, Reina Sterner, Thomas, and Cristina. And of course, the funding from the Spanish government and ERC funding. Thanks a lot for your attention, and I will be happy to answer any questions you have.
Okay, thanks very much, Miguel, for a fantastic talk. So Andrew, can I pass over to you again?
Great. Okay, we did have one question from YouTube from Olivia Lagner. What are you using to calculate the free energy versus structure plots?
What, sorry?
What are you using to calculate the free energy versus structure plots?
Yeah, to recover the free energy, we rely on metadynamic simulations, which basically during the simulation, you add repulsive potentials in order to encourage the system to jump from local energy minima to sample the other states. And after a long time, when the whole space has been covered, you basically recover the free energy by summing the Gaussian, the repulsive potentials added during the whole simulation as a function of the collective variable. That in this case is this open to closed transition.
Great. We have a couple in the Q&A panel. How long were the metadynamic simulations performed? And can you also comment on which force field is used?
Well, the force field is the amber force field, the common that is used for protein. And the time that requires to get this, well, we use an approach that is called workers, that instead of one simulation, we run 10 simulations that interact each other. It means that the worker that is adding repulsive potentials here, when it jumps to another local energy minima, knows or remembers the Gaussian potentials that has added the other workers. So with this strategy, we decrease the computational cost by 10 times, tenfold. But the accumulated data in total, it's in the system goes like from 500 nanoseconds to 1,000. And this is the accumulated time among all workers.
Great. We have another one here. When you considered that the metadynamics simulations are converged, Are there any of the mutations located near the COM domain for increasing the flexibility in the ancestral enzyme?
You mean if the simulations are convergent?
It says, I guess if you consider that the metadynamics simulations are converged, are any of the mutations located near the COM domain for increasing the flexibility in the ancestral enzyme?
Yeah, I mean, we assess the convergence by calculating the difference in free energy among the local energy minima. And in this context, for instance, imagine that if you start adding repulsive potentials in here, the difference in energy is gonna change dramatically until you start to put Gaussian potentials in the other minima. But once you are here in the diffusive region, you put Gaussian potential more or less equally. So the difference in energy between these two states remains constant. And this is what guides us to decide where the simulation is converged. And according to the COM domain positions, none of the mutations are in the COM domain. As here the COM domain is shown like a light blue. I don't know if you can see it. And we haven't tried to mutate the COM domain in this case.
Mm-hmm.